So the last talk of this afternoon session is by Calum Brown from Cambridge University.
So yeah, my name's Calum. First of all, thanks to the organisers for organising this conference. So I'm going to be talking about some recent work I've been doing with my supervisor, Rob Jack in Cambridge, and also with Katarzyna Michel, who is at the University of Warwick. So an outline for where we're heading. We've had this described to us very nicely over the last couple of weeks. You can start from a master equation, and you consider dilating this to a joint state. So you have some unitary evolution of your system and environment. And if you condition this on continuous measurements of the environment, then you have some unraveling of your master equation into quantum trajectories. And so the question I'm asking within this context is, well, if we start with a master equation which is weakly symmetric with respect to some weak unitary symmetry, then under what conditions and what are the implications of these other objects being symmetric? Okay, so hopefully I don't need to motivate you too much why we might be interested in symmetries. We're all physicists, we love symmetries. But here's some examples. But there's no longer an analogy of Noether's theorem when it comes to open systems. So we don't have conservation laws associated with our symmetries, but there's still many reasons we would be interested in them. So here are some. So first of all, what does it mean if the master equation is weakly symmetric? So this is just the master equation in Limbaugh form. And we're going to consider some unitary operator U. Oh, things have moved around a bit, but hopefully it's still clear. U, such that this is a discrete symmetry, so U to some integer power just gives us the identity. So states transform under this symmetry by this super operator, curly U. And all it means for our master operator to exhibit this weak unitary symmetry is that U and L commute. So this is equivalent to what I've written here. And I'm just going to call this symmetry condition 1. So you can write down what it means for the Hamiltonian, the jumps, in order for your Limbaugh to commute with this unitary symmetry. But for all that matters in this talk, you just have to call this symmetry condition 1. Okay, so now if we move to the quantum trajectories, so again, this has been extensively described to us over the last couple of weeks, but we start with some stochastic Schrodinger equation. This first part here is just the effect of Hamiltonian evolution. And then we have our stochastic part, which is just the back action on the system. So we have this curly J is just our action of the jump on the state. And then we're going to take a jump unraveling. So this noise term dq just takes 0 or 1. Yeah, so this is hopefully clear. But what we're going to do is we're going to consider the probability distribution that's generated by these dynamics. So for example, so we have this P of psi t. So this just tells you the probability your conditional state is in the state psi at time t. And this distribution evolves deterministically by this equation here, which I've called the unraveled quantum master equation. And so this is like a Fokker-Planck equation for the distribution of our conditional states. And it's evolved by this object here, which I'm going to call the unraveled generator. So you can write this down for any jump process, and this is what evolves our distribution. And so now we're going to consider the symmetry of this generator. So if you remember in the case of the master equation, we're just interested in when the unitary symmetry commutes with our generator of those dynamics. Now we just want to ask exactly the same thing. Because this generator, it fully determines not just the evolution of the distribution, but it gives us the stochastic process and everything else. Okay, sorry, some of my words seem to have moved around, but hopefully it's still clear. So we consider this unitary superoperator, epsilon, which acts on the distribution like this. So this is where the symmetry comes into this problem at the level of the generator. And then we want to know exactly as we did before with the master equation, when does our generator commute with this unitary symmetry? And what are the conditions on the Hamiltonian and the jumps? So in order to write this down in the most general way we can, we have to first do some grouping of jumps together. So all that this means is that we are going to consider some sets which contain jump indices. And so these jump indices are in the same set if the corresponding jumps have the same destination for all states. So that just means when you act on some wave function with your jump, this is proportional to any other jumps which are in the same set. So this collective action of the set is given by the superoperator A, which is just a sum over all jumps that give you the same destination for no matter which state you start. So these come in two types. We can either have reset jumps, which has been described in quite a lot of talks over the last couple of weeks. And so this is just some rank 1 operator where this chi alpha just tells us the reset state to which we jump, parameterized by this psi and the rate gamma. Or we can have jumps which are just proportional to one another. So you can just consider maybe some dephasing from your environment, some dephasing from your measurement apparatus, and we can trivially just combine these if they're proportional operators. Okay, so now finally we can come back to the question of when does our generator commute with our symmetry? Well, our generator commutes with our symmetry if the Hamiltonian is symmetric, That is that it's invariant under the application of the symmetry. And if under the application of the symmetry on these super operators A, they're just permuted to one another. So the total set of these super operator A's is completely unchanged. This is the condition for our generator to be symmetric. And so we call this symmetry condition 2. It's a more stringent condition than that of the master equation because our measurements have to respect the symmetry. So we can start to make a diagram of what we have. So we go from just the master equation being symmetric with condition 1 to the fact that our trajectories of the conditional state are symmetric with condition 2, and 2 implies 1. Okay. So what does it mean on the dynamics if our generators are symmetric? Well, if we just consider the Lindblad case to begin with, then you can see that if we have some initial state rho naught, then the solution of the master equation is given by this path rho of naught tau. So this just describes the solution in time to our master equation. Now, if we instead consider the symmetry transformed of this initial state, the solution to the master equation to this state is just going to be the symmetry transformed of the path we had before. So if we have some symmetric initial state, then we stay symmetric for all time under evolution with the master equation. So now everything just follows through exactly the same in the case of the unraveled generator. So we have some initial distribution, and the solution of the unraveled master equation is given by this distribution path in time. And then if we consider the symmetry transformed initial distribution, the solution is just given by the symmetry transform of this initial distribution. And again, if we have a symmetric distribution to begin with, we'll be symmetric in all time. But this also has some implication on the trajectories, the stochastic trajectories, which is that the probability of some path given an initial state is equal to the probability of the symmetry transform of this path conditioned on the symmetry transform of the initial state. And so crucially, if we have, again, a symmetric initial state, then you can see that what happens is the probability of this path is just equal to the probability of the symmetry transform path. So under the symmetry, our ensemble trajectories just map onto each other. So the whole ensemble is invariant under the application of the symmetry, so long as we have this condition up here. Okay, great. So, so far we've just considered trajectories of conditional states, but we can also consider if we want to include the measurement record. So now we're going to consider trajectories of this form. So we have the conditional state and this vector q. And if you look back at the stochastic Schrödinger equation, this is where this comes from. So this just counts all the jumps of all the different types up to time t. So this is equivalent to the measurement record. And we're going to call these labels trajectories. And these trajectories evolve with some new generator, which I just denote W dagger F. So we have the same Fokker-Planck style equation. This time the distribution involves q. And now we need to introduce, again, the associated symmetry operator. So now we again act, we call this epsilon f. We act on the distribution. We get the same action on our state. And now we do the most general thing we can to just a classical vector, which is we permute the elements. So this pi is just a permutation of this vector q. And so then we say, okay, when do we have the fact that the generator commutes with the symmetry operator? That is that these labeled trajectories are symmetric. Well, this happens again if the Hamiltonian is invariant under the symmetry. And this time, it's at the level of the individual jumps, that the action of the symmetry is just a permutation on the jumps. So the total set of the jumps is invariant up to phases. And these phases are arbitrary. So we call this symmetry condition 3, because this is more stringent than what we had before. So we add this to our diagram. We're no longer looking at just evolution on the system. We're looking at time records as well. So this guy lives down here in symmetry condition 3. So that's the end of the trajectory part of the talk. So hopefully that's clear if there's any questions. No? Great. Okay, so now we're going to consider instead, like I said at the beginning, performing a dilation of our master equation. So if we dilate our master equation, we're just considering the unitary evolution of the system and environment coupled together. And that's going to be written down by this state here, which is a continuous matrix product state. So this is just completely equivalent to what Nina described yesterday of the input-output formalism. So we have this guy is just our unnormalized conditional state based on some measurement record. You can see we're integrating here over the measurement record. And then this term here is what was described yesterday as the associated creation operators of different quanta, which is associated with a single jump. So you can imagine jump takes place, photon emitted into the environment. This corresponds to acting with a creation operator of the same type. And then this is just the one non-zero term in the Ito table that was described to us yesterday by Nina in the quantum stochastic calculus. Okay, great. So this is our state that describes the joint state, CMPS. And this evolves in time with this Hamiltonian here. So you can see we have the system Hamiltonian, and we have these jumps coming together with their associated creation operators. So now we ask the same question of this object, which is, well, when is it symmetric? So now that we're considering this on the larger space, we have to define some unitary which acts on the environment. So we could just call this UE. I'll describe in a minute what this actually is. And oh, everything's jumping around again. So the CMPS is symmetric with respect to this joint separable symmetry, U, which we considered before on the level of the system, on the space of the system, sorry, centered with UE, which we define now. That is to say that the action of this symmetry on the Hamiltonian leaves it invariant if the following condition holds. Well, we're just back to symmetry condition 1. So the condition is just that the master equation is symmetric. So what this means is that there is an if and only if between the master equation having some symmetry and there existing a UE, which is actually given by this thing here, such that the joint state, the CMPS, also has a symmetry. So do I have time? Yeah, I probably have time. So this U here, this just comes from the symmetry condition 1 that I spoke about before, that I said I didn't want to go into details of how you would actually define this at the level of the jumps and the Hamiltonian. If I just quickly explain that what you can do is if you define these traceless jumps, so this is just a new representation of your Hamiltonian, by removing the trace divided by the dimensions of the Hilbert space, then if there exists a unitary U matrix such that the action of the symmetry on your traceless jumps just mixes them, this is equivalent to this statement here. There's an equivalent statement on the Hamiltonian that I don't discuss, but effectively these two are equivalent. And so we always have this U if we have this, and then we know that if we can just use it here, there will always exist a symmetry. So this is what it means for the joint state to be symmetric. So let's just add this to the diagram. We now have a new object in symmetry condition 1, which acts on both the system and the environment. And so there's this if and only if between these two here. Great, so one final object we can consider is we can consider dephasing this joint state. So what we do is we make projective measurements in the environment on the condition on the basis of these creation operators, dBs. And the corresponding continuous matrix product operator that we get is given by this guy here. And the main thing to notice is if you look at this term, you'll see that we've lost any coherence between different measurement records. So now when we make these measurements, our measurement records have to come together in this way, and we lose coherence between different records. So you can write down some operator that evolves this CMPO. You can see it has a similar structure to that of the master equation. And you can ask in what condition this thing is symmetric, i.e. this DLT that generates our dynamics, when does this commute with the symmetry? So we have this separable symmetry. When does this DLT commute with this symmetry? Well, it turns out this occurs just under exactly the same conditions as for the labeled trajectories. That is the Hamiltonian symmetric, and our jumps are commuted under the symmetry. So this is just symmetry condition 3. So we can add this into our diagram, and we can say, okay, if we dephase the CMPS, we reach this dephased CMPO, which is symmetric at the same level as these trajectories and measurement records. And this is effectively because these objects are somewhat equivalent in the sense that the dephased CMPO can be thought of in some ways as integrating over our labeled trajectories. Great, so just to summarize, we saw that I've given the conditions for the quantum trajectories and their labeled counterpart to be symmetric under the unitary symmetry of the master equation. One thing I didn't mention is that this result comes about by considering gauge transformations on the generator. So in the same way you can ask what different representations of your Lindblad give you the same dynamics of your row density matrix, you can ask, okay, what different representations actually give me exactly the same generator. So I haven't mentioned that here, but that's in this paper here. And then you can, we also showed that where the symmetry comes from with the master equation, and the symmetry comes from the fact that there exists always this joint symmetry at the level of the dilated joint state. So one thing I haven't mentioned in this talk, but if you are interested, you can read the paper, is that as well as giving this taxonomy of symmetries of these different objects, there are applications of these things. A particularly interesting one is this eigenfunctions of the generator. So in general, it's very hard to find eigenfunctions of the generator for your Fokker-Planck equation over the trajectories, but if it's symmetric, then we can characterize all the symmetries of eigenfunctions of the symmetry operator, and these are also going to be eigenfunctions of our generator. And there's many more interesting avenues in the future for this kind of theory. So I'll leave you just with this, the picture we had before, and just say that if you're interested in reading some more, then there's also a few other objects which are talked about in the paper, which fill in this gap here. And so yes, if you're interested, you can read the paper. And there I'll finish, and thank you for your attention.
Time for questions?
Thanks for that very clear talk. So you sort of mentioned at the end the future work, but could you comment, and this, I guess this is really two questions, but I'll put them together. I mean, do you think that anything would substantially change for considering continuous unitary symmetries or anti-unitary symmetries?
Yeah, so anti-unitary symmetries, there's quite a lot more to say there. It's not so clear exactly how this follows through, more from a sense of how we prove these conditions. And so that's maybe slightly more complicated to discuss. But in terms of the continuous symmetry, a lot of this follows through. That's something we're thinking about at the moment, or thinking about doing. But in general, the same sort of conditions arise. Just you have to consider the continuous version of the symmetry parameterized by some Hermitian operator. But yeah, in general, it has the same behavior.
Yeah, so I just had a question about the order of implications.
Yeah.
So what is equivalent to what? So if I go on the upper left corner, if I have a CMPS that has all the symmetries, I guess for you the CMPS also include the system legs, like you have the field and also the system, right, is still in the symmetry. So you have two unitaries.
Yeah.
But so if the CMPS is, it seems like the strongest thing, right? To ask that this guy is symmetric, even before you do measurement on the field and choose a particular unraveling.
Yeah, so, okay, so when it comes to the symmetry of the CMPS, the statement is that for some unitary UE on the environment, I can choose this such that it is symmetric. In general, so I push some things under the carpet, which is that this symmetry might involve you pushing your state into the rotating frame. So you have to apply some quantum optics operation effectively, some shift, some exponential shift of your jump operators to move your Hamiltonian into the rotating frame to see the symmetry, or you consider a time-dependent symmetry. So you consider this UE to be time-dependent. So it is slightly more complicated there, but the point is that there exists one such that this is true. So when you trace over the environment, you recover something symmetric. But remember that you say it's the most general, and you're right, but under this full dephasing, down to the dephased CMPO, the condition is completely dependent on what measurement records I make of my environment, what measurements, I make of my environment. And so you lose all this generality, because suddenly you're talking in the realms of trajectories effectively, where it really depends what measurements you make, as to whether you retain the symmetry.
I see, but so I was understanding that the symmetry of the CMPS implies the symmetry for Lindblad.
Yeah.
But more counterintuitive that the same condition, so it would seem much harder to have the symmetry for the CMPS than for Lindblad.
Yeah, you might think so, but there always exists it.
Okay.
You just have to choose the right unitary to see it, which upon the tracing out, doesn't matter what you chose.
So, sorry if I can. So, are the proof techniques a bit similar to the classification of symmetries for MPS? The MPS corresponds to the repeated interaction setup. So here it's the continuum limit.
So the proofs, I would say it goes more along the lines of considering, it's kind of analogous to considering like the Choi matrix, this kind of direction, as opposed to for standard MPS, as far as I'm aware. I'm not, I haven't looked in detail at the MPS proofs.
Okay, thank you.
More questions? More questions? So I have a quick one. I'm not sure I got everything right, but will it make sense to think of symmetry breaking, spontaneous symmetry breaking, perhaps by looking at the eigenfunctions of the generator of steady states?
Yeah, you can think of this. I guess the difference is that really when you set your representation, you've kind of chosen your dynamics. So we're not tuning a parameter here or anything like this. We just have a particular representation which corresponds to a particular measurement protocol.
Right. Yeah. I wonder then whether there's a notion of topological defect one can introduce. Like,
Yeah, I mean, that's a good question. It's something to consider.
Well, it makes sense even. Yeah.
Yeah, for sure. I don't know is the answer. But, yeah.
Thank you. All right. So let's thank Calum again. And this closes the afternoon session. So I guess I see you all tomorrow. Enjoy the rest of the evening. Yep.